Okay, we are live on the YouTube, and I'll also start recording to the cloud. Okay, so we are live. So we are all set. Welcome to the Silicon Valley chapter of IEEE Computer Society. I'm the chapter chair, Vishnu Pendyala. Ours is the largest chapter in the Silicon Valley section of IEEE with over 4,000 subscribers in our mailing list and a strong following of over 12,400 on Twitter alone. We are uniquely positioned by the virtue of our location and available expertise. Today is IEEE Day, and I wish you all a very happy IEEE Day. According to the IEEE Day website, IEEE Day is an annual event that celebrates the first time in history when engineers worldwide gathered to share their technical ideas back in 1884. One of the IEEE Day's objectives is to show the ways IEEE members in local communities join together to collaborate on ideas that leverage technology for a better tomorrow. So here we are exploring the math in support vector machines. We'll be examining some of the mathematical intuition behind support vector machines, abbreviated as SVMs. We'll cover things like Lagrange multipliers, geometric intuition by way of Convex Hull. Then we are going to look at orthogonal functions, Hilbert Space, Duality, Hilbert's theorem, Mercer's theorem, and others in an easy to understand and appreciate approach. So the goal is for everyone to easily understand and appreciate. Support vector machines are used for supervised machine learning and have been very successful in many applications, including those like image classification that typically favor deep learning. Support vector machines owe their power to the intriguing math involved in its fabrication. So this talk will introduce support vector machines and cover some of that math. So we'll try to keep it interactive, but I will not wait for a long time to get your answers. If you have any questions, please post them in the chat window. So computer science in general and machine learning in particular is applied math. And machine learning can be seen as the interesting or the happening side of math, the exciting side of math. All the abstractness of math is put to action when used to solve advanced and interesting problems like face recognition, for instance, or stock price prediction. Support vector machines are probably the most intriguing, popular, and successful algorithm in traditional machine learning. They kind of provide the theoretical foundations to appreciate most of the machine learning, including deep learning. We will see how and why a little bit later. For instance, when we talk about kernels, we'll see that support vectors can be thought of as the hidden nodes in a neural network. Isn't that interesting? The number of hidden nodes is kind of a hyperparameter. And here we go, support vectors tell you how many hidden nodes are there in the neural network. So the focus of the talk is mainly to making sure you understand the math, then make it exhaustive treatise on calculus and linear algebra and functional analysis and algebraic manipulations. So hopefully you'll be with me throughout the presentation. So let's start. Support vector machines can be used for both classification of data or regression problems. But they are more popular for classification, and that will be the focus of today's talk. So here, for instance, there are tweets that are classified as true on the left-hand side and false on the right-hand side. And if there's a new tweet that comes in, how do we know whether it is true or false? So we can come up with a classifier, a decision boundary based on a classifier, which will help us classify the tweet as true or false. So a classifier in the simplest manner is a straight line. The decision boundary is just a straight line. It's called a linear classifier. So going with a linear classifier, and particularly since the data can be separated by straight lines. So if we consider a number of classifiers, the classification of the new tweet depends on the classifier. As you can see here, this particular new tweet is in the middle of the true tweets and the false tweets. And there can be any number of classifiers which divide the true and false tweets. So the big question is, which classifier are we going to choose? So it's anybody's guess that we want to choose a classifier or a decision boundary that is as far as possible from the both classes, from the true tweets and from the false tweets. So we want to maximize the margin between the two classes. I mean, classification can be extended to multiple classes, but we are, for simplicity of discussion, we are going to look at binary classification here. So we want a margin which is maximum, and we want this margin that separates the two classes to be as wide as possible. And the decision boundary is basically the line dividing the margin, the maximum margin, as you can see here. So that should be our goal, right? So there's a little bit of terminology here, interesting terminology. Why is it called support vector machines? So the reason is this. So you can see the support vectors as supporting the margins, the two lines separating the classes, right? So these vectors, I mean, each data point is a vector. So in machine learning, every row in the data set becomes a vector in space, right? So the vectors or the data items which fall on the margins are called support vectors. You can think of them as supporting the margins, right? They're like pushing the margin. So that's an intuitive way of understanding support vectors. So based on the support vectors, we come up with the decision boundary, and we classify new data points. So in this case, the new tweet falls on the false side. So false side of the decision boundary. So that's why it can be classified as false. So the idea is to come up with the maximum margin separating the two classes, and the decision boundary divides the margin into two equal halves, and the vectors falling on the margins are the support vectors. So now, an interesting finding is, do the points circled in red impact the classification of a new data item? The answer is no. Why? Because the maximum margin is identified by the support vectors only. We don't care for any other point in the data set. We only care for the points on the margins, the support vectors. So what does that tell you? So that tells you that even if there are a million rows in your data set, and if there are only 5 support vectors, all we care is the 5 support vectors. We don't care for any of the other data points. So in terms of an analogy, you can think of the maximum margin classifier as an arbiter, right? So an arbiter tries to be as away as possible from both the sides, right? A judge, for instance, a judge in a court of law will try to be away from both parties as much as possible. So you can think of the classifier like that. It is away from both classes as much as possible. So that is broadly the summary of support vector machines, a very high-level overview of support vector machines. But the fun part is in determining the margin. So the geometric intuition of the support vector machines algorithm can be thought of as drawing convex hulls around the points, around the classes of points in the training data set. So a convex hull can be thought of as a rubber band. Say these are all the pins on both sides of a board. And then you are given a rubber band, which is tight enough to go around the pins. You will probably end up in a shape like this. So that is the intuition of a hull, convex hull. Why is it called convex? Because convexity is an important property in geometry and also an important property in machine learning as well, traditional machine learning particularly, because most of the optimization that we are going to do in machine learning is convex. So the intuition is that both sides of the data points form convex hulls, right? And the points are linearly separable only if convex hulls do not intersect. So only if you are seeing two convex hulls here. So only if these two convex hulls do not intersect can we separate them with a straight line. If they intersect, you can visualize easily. They are not linearly separable. So, by the way, convexity means in geometric sense or in machine learning sense as well, convexity, a convex shape is one in which you take any 2 points on this shape and join them. Take any 2 points P and Q and join them. That line connecting P and Q should be within the shape, right? So if you look at this shape, this is a convex shape. So you take any 2 points and connect them, it would be within the shape. When is a shape not convex? When it is dented, like somebody has eaten into it. Suppose this point was inside and we somehow draw the boundary like this. Then if you take points here and here, the line joining the 2 points wouldn't be inside the shape. So that would be non-convex shape. But in machine learning, mostly we deal with convexity, right? So this is a two-dimensional visualization of the training data set. What if there are several dimensions? So in that case, the convex hulls can be thought of as polytopes. So a polygon in multiple dimensions is called a polytope. And the maximum margin can be thought of as the polytope distance, the distance between the two polytopes. So basically, you draw a line connecting the support vectors on the polytopes, and the distance between that gives the distance between the polytopes. And the decision boundary will be perpendicular to it and divide it into two halves. So that is the geometric intuition. But the next question is, what is the length of the maximum margin? So, I mean, we can try to find convex hulls and find the support vectors through the convex hulls and determine the margin and all that. There are algorithms to find convex hulls of a given set of points, which are not too, in terms of the complexity, it's not too hard. but still they may not scale. The solutions may not scale well to our machine learning kind of big data problems. So that is the reason why we need to evaluate alternate methods of finding the support vectors and the maximum margin. So, given two parallel lines, so let them be ax plus by plus c1 and ax plus by plus c2. To simplify the discussion, we'll only consider the two-dimensional case in the beginning, and we'll extend it to multiple dimensions. So take two parallel lines, the dotted lines on either side of the solid line. So think that they are ax plus by plus c1 and ax plus by plus c2 is equal to 0. So how do you find the distance between two parallel lines? So this is a simple geometry problem, which we would have studied in our elementary or middle school, probably, or high school. And the answer is the distance between the two straight lines is given by c2 minus c1 divided by the square root of a square plus b square. So in machine learning, what are A and B? A and B are probably the weights, right? We all know linear regression, linear classifier, logistic regression. So the features, the feature vectors are, the coefficients of the feature vectors are basically the weights. So A and B can be thought of as the weights of the features. Then what is a denominator? So denominator is basically the norm of the weight vector, right? The norm of the weight vector is given by this. If W1 and W2 or A and B are the weights, the norm of the weight vector A comma B is basically square root of A square plus B square. So that's the norm. So now let us extend the same thing to our machine learning parlance. So this is all geometry, A, B, C, this is all geometry, but we want to express it in terms of weights and biases. So how do we do that? So the margin, so first thing is any equation for the margins. So the margins are called H1 and H2 here. Any equations for H1 and H2 can be brought into these forms shown on the slide, right? So the left side can be represented as Wx plus B is equal to -1, and the right margin can be represented as Wx plus B is equal to +1, where W is the weight vector and X is the feature vector. And the line, the decision boundary itself, the maximum margin classifier itself can be represented as Wx plus B is equal to 0. So why is that the case? Because you can easily adjust the coordinate system, right? Suppose this was not 1, this was say 10. You can adjust the coordinate system, right? Such that this distance is just -1. If it is 10, then you adjust the x-axis scale and the y-axis scale such that this is -1. Or you could do some algebraic manipulations. But there's no loss of generality when we assume that the equations of the margins are these and the equation of the decision boundary is this. Right? So when this is the scenario, the margin, if you look at the previous slide, from the previous slide, is C2 minus C1 divided by the norm of the coefficient vector, right? So C2 minus C1 is basically 2. 1 minus -1 is 2. So the numerator is 2 and the denominator is the norm of the weight vector. Now there are some constraints. What are the constraints? We want to classify the point. The classification is given by fx. We want to classify the point as a +1 if it is on this side of the margin, and as -1 if it is on this side of the margin. So in algebraic terms, if wx plus b is greater than or equal to 1, so that is the right hand side, the prediction will be +1. And if it is less than -1, the prediction will be -1. So that's the idea. So we have an optimization problem. So we need to maximize this margin. And these are the constraints. So the objective is to maximize the margin, which is equivalent to minimizing the reciprocal, right? Maximizing 1 by x is same as minimizing x, right? So that's what is happening here. And to simplify it further, we want to avoid square roots. If you have square roots and all that, math will be a little more complicated. And fortunately, square root is a monotonically increasing function. So whether we maximize the square root or without the square root, it's the same, right? If we are trying to find the w for which the norm is minimum, or the margin is the maximum. So we can just proceed with the reciprocal and also taking the square of the norm, right? Because the square root is monotonically increasing. So the maximizing the margin problem is equivalent to minimizing the reciprocal, which is the norm square by 2. And the constraints we have are wx plus b greater than or equal to 1, wx plus b less than or equal to -1 for these classes. Now, these two inequalities can be easily combined with this inequality. Why is that so? You just substitute the values into this. When y is equal to 1, yi times wx plus b is greater than or equal to 1. That is the first inequality. And when yi is equal to -1, you have the same inequality holding good, right? You multiply yi with the wx plus b, it is still greater than or equal to +1. So this is a constrained optimization problem. Therefore, we need to use Lagrange multipliers to solve the optimization problem. So what is Lagrange multiplier method? So the geometric intuition is given in this figure. Suppose we want to maximize a function fx, where fx is x plus y is equal to k. Subject to the constraint, any constraint, a convex constraint, hopefully, because we want to deal with only convex shapes in machine learning. A convex shape, say g of x comma y. So how do we do that? What is the intuition? How do we simplify this? So we can vary k. So that is the purpose. So we want to find out x plus y. We want to maximize x plus y such that g of x comma y is satisfied. So that means the point should obviously lie on g of x comma y. And the point should also lie, the point for which the x comma y point for which x plus y is maximum, such that g of xy is equal to 0, should lie on the constraint g of x comma y and also on the straight line x plus y is equal to k. So when does this happen? So this is a very common scenario, right? You take work-life balance. We have only certain number of hours in a day that we need to optimize. So that you can think of as x as work and y as life. So there's a constraint. You have only 24 hours in a day. So these are very commonly used. This is a common scenario, and Lagrange multipliers is commonly used method for solving these kind of optimization problems. So how do you determine the optimum value of f of x comma y? So if the line is above the constraint g of x comma y, it's not going to help, right? Because the constraint is not met. If the line goes below g of x comma y, then it intercepts the constraint curve at probably 2 places, but those 2 places are not optimum. So the optimum is when the slope of this line is the same as the slope of this point. So when this line touches this point, both the slopes are equal. Now, in univariate calculus, slope is given by the derivative. But in machine learning, we are talking in terms of several dimensions. So when there are several dimensions, the slope is the gradient, right? Gradient is basically the vector. So if you can, so this is the gradient. So it is basically a vector of partial derivatives. Partial derivatives of the function with respect to each variable. So if x1, x2, x3, xn are variables, so we take the partial derivatives of f with respect to each of the variables. So that is the gradient. So as you can see, this is a vector in itself, right? So that is the idea. So we want the gradients at the point where we achieve the maximum for x plus y, or maximum for f of x comma y, to be equal to the gradient of g at that point. Now, remember, these are vectors. So what does that mean? Vectors have both magnitude and direction. So do we want the magnitude also to be the same? Probably not, right? We are only concerned about the direction. We only want the direction to be the same. So we multiply the gradient with a, it's called a Lagrange multiplier, lambda, because we want only the slopes to be same, but not the magnitudes. So this equality represents the Lagrange formulation of the optimization problem. So we basically want the slopes to be equal, and the slopes are basically given by a vector, which is called the gradient. And because the gradients need not be equal in magnitude, only direction, we have this lambda to indicate that the magnitude can be different. Only the direction needs to remain the same. So that is the idea. So a few questions before we proceed further. So given 2 quantities f and g, how do you assign them relative importance? I mean, that's the whole idea in machine learning, right? We assign relative importances to features. So what is the mechanism to do that? We use weights, right? So we use weights, say W0 and W1. The first quantity is weighed by W0 and the second quantity is weighed by W1. So what if none of the g is desirable, but all of the first quantity is desirable? How do we do that? So we basically want all of f, that means f, and we don't want any of g. So we subtract minus W1g. I mean, we could assign W1 is equal to 0 so that the g is completely disappearing. But the thing is, we want to also meet. We want to meet g. I mean, g should also be obeyed, right? We don't want to exclude g completely from the picture. We want g, but at the same time, we don't want it to the extent possible. So what we do is we do f minus W1g and make W1 very large. So W1g basically, in that sense, acts like a penalty term, right? So W1g is a penalty term which will be penalized, which will penalize the term f minus W1g. when we want the G to be as minimum as possible. So the next question is, does this hold even when f and g are functions? The answer is yes. It is not limited to vectors or just single scalar quantities. It is this will hold even for functions. So fx comma fx minus w1 g, g of x can be considered an objective function that needs to be optimized if optimal x has to be determined. So in general, if we want to optimize fx under a given constraint gx, we consider fx plus some function of gx, right? We don't know what that function is. And we want that function h of gx to be 0 if g of x is followed. If the constraint is met, then we want this function to be 0. And if the constraint is not met, we want this function h of g of x to be infinite, so that it will penalize. It will make it very difficult for this term to be minimum. So if you look at it, h of g of x is a step function. When g of x is not met, it is 0. And when g of x, when g of x is met, it is 0. And when g of x is not met, it is infinity. So it's like a step function. But step functions are not easy to handle, particularly in calculus and things like that, right? So you want a smoother interpretation. What is a smoother interpretation of a step function? So if you remember logistic regression or fuzzy logic, you would recollect that a sigmoid function kind of represents kind of approximates a step function, where the sigmoid function is in the shape of an S, right? Another way to look at it is as a straight line, right? This S shape can be approximated by a straight line. If g of x is met, it is still 0. And if g of x is not met, then this line, the straight line, will tend to infinity anyway, right? So why not approximate h of g of x with a linear model? So h of g of x is basically a constant times g of x, right? In this sense also, we can represent the objective function. So remember the objective function, rather here in the previous slide. So we can represent it as fx plus or minus a constant time g of x. So h of x being alpha times gx, we can represent the objective function as f of x comma y minus alpha times g of x comma y minus c, because we are assuming that the constraint is of the form g of x comma y is equal to c. So our goal is to find x, y, and alpha by minimizing or optimizing. It could be minimum or maximum, but we want to find the optimum value of this function subject to this constraint. So we need to determine x, y, and alpha, right? So for optimization, we all know that we need the derivative to be equal to 0. Because this is multivariate calculus, we don't go with simple derivatives, we go with partial derivatives, and we consider the gradient instead of the simple derivative. So we want the gradient to be equal to 0. So when the gradient is equal to 0, so remember the gradient. So we want, if this gradient is equal to 0, each of the elements of the gradient will have to be 0 as well, right? So we can simplify the notation a little bit by calling the partial derivative of L with respect to alpha as delta alpha. So as delta alpha, and partial derivative of L with respect to x as delta x, and so on and so forth. So partial derivative of L with respect to alpha, the first term, there's no alpha term, right? So it becomes 0. So the first term derivative becomes 0. Now the second term is basically alpha, the coefficient of alpha here. So derivative of k times x is basically k with respect to x is basically k. So in this case, derivative of alpha times this constant, because there's no alpha, we can consider this as a constant. So then we get minus g of x comma y plus c is equal to 0. So that is the first equation. Now the second equation is when we take the partial derivative with respect to x, we get, remember x is appearing in both the terms except for the last term. So we get the partial derivative of f with respect to x minus alpha times the partial derivative of x with respect to g, and equate that to 0. And the third element of the gradient is the partial derivative with respect to y. So when you take the partial derivative with respect to y, you get this expression. So instead of x, you have y. That's it. So that's the only difference. So from 2 and 3, you can easily see that the gradient of f x comma y, there's no alpha. Remember, f is a function of x and y. So the gradient of f is equal to alpha times the gradient of g. It matches with our initial intuition, right? The slopes are matching, and therefore the gradient of f should be equal to gradient of y. Gradient of f should be equal to gradient of g. So that's matching with our intuition, right? So now let us go back to support vector machines. So that's our Lagrange multiplier method. So what are f and g in support vector machines? So f is our reciprocal of the margin. You can think of it as a loss function L, which is the squared norm divided by 2. And not exactly the margin, but the square of the denominator, right? So that is f. F is basically the squared norm divided by 2, and g is basically this inequality. So we combine y and x into one single inequality, and then we get this inequality. Now the question is, how many constraints are there in our support vector machine formulation? So if you look at, so whenever these questions come, you can feel free to, when you're watching the video, you can feel free to pause the video and then think a little bit and answer. But for this presentation, I'm not going to wait for the answers in the interest of time. So how many constraints are there in our support vector formulation? There are n, right? If you look at the g above, this is g, right? So I is equal to 1 to n. So there are g such constraints. For every I value, there is one such constraint. And we should also remember that x and w are vectors and not variables. But fortunately, the calculus does not change a whole lot at quite a few places. It will change at some places, but not a whole lot. Now, this is different from our previous slide. How is it different? First thing is, in the previous slide, it was inequality. So if you see this in the previous slide, g of x comma y was an equality. Sorry, g of x comma y was an equality, and there was only one constraint. But in the support vector machines case, we have inequality instead of equality, and there are n such inequalities. So it's a new scenario. What do we do now? So support vector machine constraint is an inequality. So instead of inequality, we have inequality in G. So there is something called KKT conditions. So we impose Karush, Kuhn, Tucker conditions on X, Y, and alpha, right? So these are simple conditions, though the name is a little bit sophisticated, but the conditions themselves are quite simple, as you can see here. So we have our first equality, which is a loss function, which is equal to f of x comma y plus alpha times g of x comma y. This is the Lagrange way of optimization under constraints. Now, because we already know that the gradient of L is equal to 0. By the way, this symbol is nebula. The symbol used for gradient is nebula, but we'll just call it gradient, doesn't matter. So gradient should be equal to 0. Why? Because we are trying to optimize this L. And now we have an inequality, which is g of x comma y is less than or equal to 0. So that's the third inequality. And then these are coming from the KKT conditions. First thing is that alpha should be greater than or equal to 0, which is quite intuitive, right? We are trying to minimize f. So alpha needs to penalize the term. So it needs to be infinite, right? I mean, when G is not obeyed, the constraint is not followed, then alpha needs to go to infinity. So that's the reason why it has to be positive. If it is negative, then it goes the other way around. So alpha is greater than or equal to 0. I mean, this is just intuition, but it's called, it's formally proved in the KKT formulation. And then alpha times g of x comma y is equal to 0. This is also an important observation from the KKT conditions. But again, it is very intuitive, right? Remember, we talked about it. If the constraint is met, then we anyway want this term to be 0. So it is quite intuitive, but it has been formally defined this way by the KKT condition. So all these are, if you look at them, they're all intuitive. Even the previous slide, the Lagrange multipliers and all that, it's basically intuition. There's nothing great, but they have been formally defined and proved by these mathematicians. Now, so if you look at 5 carefully, for support vector machines, the constraint is strictly obeyed, right? The g of x comma y will be equal to 1, or rather g of x comma y will be equal to 0. If you look at let us go back to the equations of support vector machine. So if you look at the or rather, let us look at the lines. So if you look at the equations for the margins, for support vector machines which lie on the margins, these equations hold. That means Wx plus b is equal to -1 if the support vector is on this margin, and Wx plus b equal to +1 if the support vector is on the other margin. So the constraint is strictly holding. So what does that tell you? So it tells you that g of x comma y will be equal to 0 for the support vectors. So remember, for these support vectors, this is equal to 0. So for support vectors, g is 0. That means for non-support vectors, alpha has to be 0, because g will not be 0, alpha has to be 0. That's a very powerful observation, right? So what does it tell you? Even if there are like a million rows, we are concerned only the alpha values for the support vectors, which could be 5 or 6 typically, right? So now the other thing is, if there are multiple constraints, g of I, each will have Lagrange multiplier alpha, and the second term of L will be a summation, right? It is quite intuitive as well, right? Remember all the discussion that we had here, how W1 plus G is a penalty term. If there are multiple G's, we'll just increase the number of penalty terms for each of the constraints. So that's all we are going to do. So, so that's the thing. So now a few more questions to ponder and understand the intuition. So what is the goal of x and y with respect to L in terms of x, y, and alpha? So the goal is to minimize L of x comma y comma alpha, right? So that is our goal. We want to minimize the loss. Of course, we are still using x comma y. We are not yet in the w and x notation. We are still understanding the intuition. Now, what is the goal of alpha with respect to L? It does the opposite, right? The penalty term does the opposite. It tries to maximize the loss. So if the constraint is not met, it will go to infinity. It will try to make the function infinite. Now, did we encounter a similar kind of scenario? Actually, at many places. So one of the examples is in the generative adversarial networks, which are very popular these days, right? So these kind of min-max problems are pretty common these days. It's actually a game theory problem. Something is trying to minimize and something else is trying to maximize. One player is trying to minimize, the other player is trying to maximize. So these are quite common these days. So the question is, when do min-max problems stabilize? So when there is a meeting ground, obviously, right? Two players are trying to do the opposite. So when does it stabilize? When they meet, there's a common ground. So minimizing L with respect to x and y is same as maximizing L with respect to alpha. When this happens, the model stabilizes. Excuse me. So argmin of L, where x and y are the arguments, is same as argmax of L when alpha is the argument. So that is the idea. So when these two are equal, when there's an equality like this, it is called strong duality. So it is illustrated in this figure. So strong duality is when these two curves touch each other. So one curve probably represents L, which is with respect to W, I mean x comma y comma alpha, or in our case, W comma B comma alpha, weights, bias, and then alpha. Right? So this is called the primal problem. So minimizing the loss function with respect to weights and biases is called the primal problem. And minimizing the loss with respect to alpha is called the dual problem. Just a terminology. It's not anything too complicated, but it's just a terminology. Later we'll see that it's just a matter of interpreting rather than any math involved, because math is just the same. So we'll see what I mean in a bit. So some more questions to ponder. So what is the abstraction for something that can take finite number of values? So something that can take finite number of values, we all know, is a vector. So it will take x1, x2, x3, so on and so forth, where n is finite. Now, what is the abstraction for something that can take infinite number of values? So this, just think a little bit. So what is the abstraction? It is a variable, right? A variable can take infinite number of values. Now, what is it that can take infinite number of values that obey certain properties? So now it gets a little more interesting. And the answer is a function, right? So a function is well-defined, is more well-defined than a variable. So in that sense, you can view functions as infinite dimensional vectors. So we started with vectors, and essentially functions are basically infinite dimension vectors. So instead of discrete values, we have continuous values. Or the other way to look at it is from the bottom. A vector can be viewed as a discretized function. You just sample the function at certain places, you get discrete values, you get a vector of the samples. So that is the third interpretation of vectors. So the first interpretation is vector as a set of numbers like this. Second interpretation is a point in space with the magnitude and direction. And the third interpretation is like a function. So if you're not convinced, here's another slide for you. So if you draw a bar chart with, say, 6 dimensions, it might look like this. Now, in the same space, if you try to fit 17 dimensions, so 17 numbers, it might look like this. Now, if you try to fit infinite numbers, infinite dimensions into the same place, they might look like a solid mass of curved mass, right? So it's basically like a function. So this is quite similar to the PMF PDF in probability, right? Probability mass function versus probability distribution function. So one is discrete and the other is continuous. So PMF could be something like this and PDF could be continuous like this. So essentially, that's the idea of a function space. So just like in vector space, you have basis vectors. In function space, you have basis functions and things like that. A typical example is, I'm pretty sure almost all of you would have heard about Fourier series, right? So what is Fourier series doing? It is basically breaking a given function into basis, right? You express the function, you're extracting the components of a function in terms of the basis. So that's Fourier series is like one kind of basis that we have in the function spaces, right? So similar ideas that we have in vector space can be applied to the function space as well. So because a vector space is discrete and function space is continuous and infinite dimensions, summation in vector space is represented by sigma, and in function space becomes an integral. And norm in vector space is given like this. The pth norm is basically the pth root of the summation of the pth powers of the norm, right? The same concept applies to functions as well. Instead of the summation, we just replace it with an integral symbol. So, and similarly, the inner product also same thing. Inner product is sigma u times v. Actually, inner product, many people use dot products and inner products synonymously, but there is a difference. Inner product, actually dot product is one type of inner product. Inner product, the definition of inner product is much more general. So the function, so that's why it applies to functions as well. So inner product has to follow certain properties. We are going to talk about it in a subsequent slide. But as long as the two entities follow those properties, we call it an inner product. So for functions, the notation is the same, but we are going to use an integral symbol instead of the summation symbol. Orthogonality is also the same. Where does orthogonality come into picture in function spaces? When defining basis, for instance, right? You express a function in terms of the basis vectors or basis functions in case of function space. So the basis functions have to be orthogonal. They must be perpendicular to each other. So how do you define orthogonality of functions? You define it like this. The inner product, which is given by the integral of the two functions, is equal to 0. And the bases basically are orthonormal vectors, and in this case, these are orthonormal functions. So, so the norm is essentially generalization of the magnitude, and the inner product is a generalization of dot product, and so on and so forth. So as you can see, we have extended the vector space into function spaces. Now, the dual, the interesting part is, remember we talked about primal and dual. Now the dual is in Hilbert space. What is Hilbert space? Hilbert space is helps you work with infinite dimensions, right? So there is this concept in functional analysis called topological space. So in fact, this will be useful for quantum computing also. A lot of stuff that you study for machine learning will be useful for quantum computing as well, the linear algebra part and the functional analysis part. So topological spaces basically express the relationships between points in the space. So you can think of space, and the equivalent of space in algebra, geometric space in algebra, is a set, roughly. You can roughly think of a space as a set of elements which follow certain properties, right? So we all know Euclidean space, right? So Euclidean is a metric space where we define the distance metric, right? So similarly, Hilbert space can deal with infinite dimensions. You can think of them as infinite dimensional Euclidean spaces, where we can work with real or complex numbers. But for our today's discussion, we'll restrict ourselves to real numbers. And in the Hilbert space, the main thing is it's a complete space. That means there's no discontinuity, it is continuous. And in the Hilbert space, it follows certain, the inner products follow certain properties. They satisfy certain properties. So basically, Hilbert space extends the concepts we use in vector algebra. So from limited number of dimensions, say 2 or 3, to infinite dimensions. So that's the power of Hilbert spaces. Now let us go back to our problem. So our problem in support vector machines is to minimize the loss function. So the general form of the loss function we studied in Lagrange multipliers is f of x comma y plus alpha times g of x comma y minus c. We have to minimize this, subject to some KKT conditions and stuff like that, if it is inequality. So we just substitute the values of f and g for our support vector machine. So f, we remember, is the norm square divided by 2, and g is the constraint. What is the constraint? Yi times wx plus b should be greater than or equal to 1. You can write it as 1 minus this thing. And then alpha is the Lagrange multiplier. So, so now applying the KKT conditions and doing the math, start doing the math. First thing is we need to equate the gradient of the loss function to 0. So that means the derivative, partial derivative with respect to w has to be 0, with respect to b has to be 0, and with respect to alpha also has to be 0. So first take w. So when you take with respect to w square, take the derivative of with respect to w, it will be 2 times w. So 2 and 2 cancel out, so you get w here. And here, this is with respect to w. So the first term, there's no w. So this is constant So the first term in the summation is a constant. The summation will remain like that. From I is equal to 1 to n, the summation remains. But this first term will cancel out. It becomes 0 because we are taking derivative with respect to w. And the second term will be alpha times, remember alpha times yi times wt times xi. So this is with respect to w. So it will be alpha I times yi times xi. This can be considered as the coefficient of w. So it's vector calculus. So wt with respect to w will still be the coefficient, right? So w minus so we eventually get w minus the summation of alpha I times yi times xi is equal to 0. That means w is equal to alpha I times yi times xi. And the classifier itself is basically the sine of wx plus b, which is equal to sine of, you just replace w with this term. You get all that stuff, and with x multiplied with x plus b. Now, how do you find b? Remember, b is also a variable. Instead of taking the derivative with respect to b, even if we take the derivative with respect to b, it will be difficult to find b, right? Because your b will be eliminated, probably. So another way to find b is look at the support vectors. For support vectors, this equality holds good. Wx plus b is equal to yi, right? If they are on the left margin, this is -1, yi is -1, and the right margin, this is +1. So this equality holds good on both cases, in both cases. So you can use that to substitute the value of w here, and then move this wx to the right hand side. So b is equal to yi minus wx, and w, replace the value of w with what we derived here, you get this expression. So if you noticed, x's are in red and highlighted. Why? The observation here is that x's are appearing together as a dot product. They are not appearing individually anywhere in whatever we are deriving. So that observation comes in very handy, right? So, okay, the second derivative is with respect to b. We take the partial derivative of L with respect to b and equate it to 0. We get alpha I times yi. The summation of that is equal to 0. So we'll use these findings later. So this is the primal part. We are taking the derivatives with respect to w and b. Now in the dual part, we take with respect to alpha, right? The goal is to maximize L, but still, whether it is minima or maxima, we are still going to take the derivative. So when we take the derivative, we get, we can write the loss function as half times w transpose times w, right? Because w square is w transpose times w. And just replace the value of w, I mean, not yet, but just simplify this summation here. So you get this first term, alpha I times 1, becomes a summation of alpha I. And the second term becomes a minus alpha I times yi times wt transpose times xi. So this second term in this summation becomes this. And then the third term becomes this. So in this expression, we are going to substitute the values of w. And also the observation that we had from the previous slide, alpha I times yi is equal to 0. So when we substitute that, we get, you also simplify it. We get L in terms of alpha I, alpha j, yi, yj, x transpose times xj. So what we are essentially doing is we are multiplying. How did we arrive at this? This is like multiplying two summations. So for instance, how do you multiply a plus b plus c? First summation, and second summation is d plus c plus f. You get all combinations of a, b, c, and d, e, f. So same thing is happening here. Alpha I times alpha j. So two summations. One is on I, other is on j. So you get all the possible permutations and combinations of the variables here. Again, we see that the x's are appearing in pairs. So that means it's a dot product. Nowhere in our derivations, whether in primal or dual, are we encountering feature vectors individually. They're all appearing in dot products. So that is a cool thing. So now what are we going to do now? We'll end up in several equalities like this, because remember I and j, we are iterating on I and j, so we'll end up in several equations, and probably it's a good time to hand it over to the software, right? There are plenty of good software packages which do quadratic programming for you. I particularly found this interesting. Somebody put up a Jupyter notebook for optimizations, and particularly optimization strategies for support vector machines. It's a very interesting work. You can probably take a look at later time. But basically, we give those equations that we derived in the last two slides to the quadratic programming software, or there are algorithms like SMO, sequential minimal optimization, to solve for alphas. Now, at optimal solution, the data items correspond to non-zero alphas or support vectors. Remember, we are trying to optimize, and when the L is optimized, we determine the alphas, and at that, for those values of alphas, the data items for which the alphas are non-zero are the support vectors. Remember our KKT conditions. So in the previous slide, for all the i's and j's for which alphas are non-zero, those xi comma yi and xj comma yj will be support vectors. All other alphas will be zero from the KKT conditions, right? So that is a big thing, big thing. We are down to just a handful of alphas. Otherwise, we would have had to deal with tons of alphas. As many rows are there, we would have had to deal with that many number of alphas. So here, we are paying attention to just a limited set of data items. So that is the interesting part. Limited set of data items. So just like in attention model, some of you might be familiar with the attention mechanism in transformer architecture in NLP, right? Natural language processing. So Google search has improved a lot after this paper, right? Attention is all you need. So where the attention is paid only to a few fixed word, although the sentence is very long, the next word depends only on a few words. So that is a whole idea behind attention mechanism. So similar to that, in support vector machines, we are paying attention to only the support vectors, leaving thousands and thousands of other data items. So we essentially converted a problem in terms of the weight vector W and bias B into a problem in terms of Lagrange multipliers alpha, right? So we eliminated W and B. So that's an important thing. Even if you had thousands of features, we didn't have to find the weights for each of those features. Because if we find the Lagrange multipliers, we will be able to classify a new data item, knowing the Lagrange multipliers and the support vectors. So feature vectors xi and labels yi are already known from the training data set, right? Since the variables in our problem changed, resulting in a dual, instead of minimizing L with respect to W and B, we must now maximize L with respect to alpha. So the original problem is actually equivalent to minimum of, it's a min-max problem now, right? So this is kind of summarizing what we already talked, right? So now the interesting part is the observations, right? What are the observations? When we use the Lagrange trick, quadratic programming, and duality, we notice that all the equations have only dot products in the data instances. Nowhere will we need the individual values of the features. So classification is anyway about pairwise similarity, right? That's what we do in any other classification algorithm also. The key idea is similarity, right? So this finding really comes in handy when we consider nonlinear support vector machines. So I have some slides on, okay, let me quickly cover this also. So you can view the objective function of support vector machines as a sum of a regularization term and a loss function. So when you plot this loss function, it looks like a hinge, right? That's how we started, right? It has to be 0 when the constraint is followed, and it has to go to infinity if the constraint is not followed. That's why we get a hinge, and that is the loss, right? It's called hinge loss. Now the first term is regularizing the weights. So when you regularize the weights, you are trying to minimize, make the weights as minimum as possible. Why do you want to make them weights minimum? Because we want the model to generalize well. If the weights are large, even a small change in the feature set will result in a change in the class, possibly. That is the reason why you want to minimize the weights. And the first term is essentially doing that. And that process of minimizing the weights is called regularization. So the SVM objective function has a regularization term and a loss function term. And the objective function is basically sum of the convex functions, which is also convex. Why are both convex? You take any 2 points and join them. The line will be within the shape, right? Any 2 points, this point and this point, straight line. This point and this point, it's within the shape. So that's why both are convex, and the sum of convex functions or convex shapes is also convex. Now a little bit about hinge loss. So you look at these values. Now, if the prediction is say 1.57 and the actual is 1, the loss is 0, right? Because the point lies on the rightmost side of the right side of the margin, and there's no loss, right? When the point is within the margin, that means the predicted value is 0.93. So if it is 0.93, what does it tell you? Remember, if it is less than 1, it is within the margin, right? Wx plus b, if it is less than 1, it is within the margin. So this point is within the margin. Now, interestingly, although the point is within the margin and properly classified by the decision boundary as 1, there is a loss, right? There's a loss of 0.07. So what does it mean? For all the points within the margin, the test data points within the margin, there is a loss. although the decision boundary is able to classify them correctly, there is still a loss if the points fall within the margin. So this is an important thing to remember. So you can do similar kind of calculations for the other two rows to understand the way Hinge loss function works. Now there are various loss functions such as the one we saw. I mean, the simplest loss function is a 0-1 loss function, where the loss is 1 when it is incorrectly classified, and the loss is 0 if it is correctly classified. That is the simplest loss function, but it is not very helpful. So that is the reason why we come up with Hinge loss in support vector machines, the exponential loss in boosting kind of algorithms, and then the logistic loss in the in some other algorithms like logistic regression. So there are multiple loss functions, but for support vector machines, we go with the Hinge loss function. Now, the question from this slide is, this data is linearly separable, and if you apply support vector machines you learned so far, you will probably end up in a classifier like this, in a decision boundary like this. But there could be another line, decision boundary drawn like this. So which of the two you think is better? Obviously the second one, right? Because the margin is wider. That means the model is regularized very well. It will generalize well. So all the good things are there in the second model. But our support vector machines results in the first model. How are we going to fix this? So, so as you can see, the margin is really narrow with support vector machines that we learned so far. But this one is better, but one constraint is violated, right? So this blue point is misclassified, but still the model is really generalizes well. So in general, there is a trade-off between the margin and the number of mistakes on the training data. So this is a key observation. So how are we going to handle this? So can we cut some slack? Can we introduce some slack into our strict boundaries? So like, can we accommodate this kind of decision boundary? Is a question. So if you carefully observe the slide here, you can notice there are 4 kinds of points, particularly of interest. So what is the first kind of points? Those are correctly classified points on either side of the margins, right? So for that, there is no, the constraint is obeyed and all good. There's no need for any slack. Now, for the support vectors as well, the constraint is strictly obeyed and there's no problem at all. They are correctly classified. So no worries. Now, the third category of points are the points which are classified correctly by the decision boundary, but are on the other side of the margin. Remember, Hinge loss gives you a loss even for these points. So for those points, we introduce a variable called zeta, zeta is. So those are the slack variables, and these zetas lie between 0 and 1, right? Because the distance between the decision boundary and the margin is 1. So these slack variables are between 0 and 1, right? So we introduce slack variables like this. Now the category 4 is when the points are misclassified, but are within the margin, right? So they are on the wrong side of the margin and incorrectly classified. So that's the third, that's the fourth category. So for that, the slack variable will be greater than 1. Remember, this is a slack variable. It will be greater than 1. So that is the fourth category. So let us accommodate the slack into our formulation. So we, instead of minimizing just this weight vector square by 2, we are going to add a slack term. Once again, this slack is like a penalty term. The slack term is basically like a penalty term. It's a constraint. So C is like a cost that you're imposing for the model not obeying the constraints. Remember, these points do not obey the constraints. So it's just like Lagrange multipliers. So this C term tries to maximize this function, this whole objective function, whereas W tries to minimize this whole function. So it's again a min-max kind of problem. And the constraints will also accommodate the zetas. Instead of 1, we are going to accommodate, we are going to say 1 minus zeta to accommodate the slack. So with this inequality and the objective function, we repeat the entire Lagrange multipliers logic and derive the expressions for our alphas and things like that. So some observations to make. So as C, if the constraint, zeta is basically violation of a constraint, right? So if the constraint is violated, we want C to go to infinity, right? Or putting it in the other way, C will tell you how much error is bearable. So as C tends to infinity, zetas will tend to 0, right? So that is the whole idea. C will try to maximize this, and W will try to minimize the whole expression, so thereby minimizing zeta. So C, when it is infinity, it's almost like hard margin. So it is like our conventional support vector machines, which will not tolerate even a single misclassification, right? When C is equal to infinity. On the other hand, when C is small and as it tends to 0, it accommodates more and more slack. So that is the idea of C. So just rethink the Lagrange logic intuition that we developed in the past few slides and apply it to this expression. You'll understand for yourself in case you are not clear yet. So when C is high, it will classify all the data points correctly. If C is infinite, it will classify all the data points correctly, and it will probably overfit as well. But when C is less, it will accommodate some slack and increase the margin. So that's the trade-off we have, increasing the margin versus stress on classifying correctly. Okay, now let us walk through the interesting part, nonlinear support vector machines. So when the data cannot be separated by a single hyperplane, that means the convex hulls are intersecting. So what do we do? So just an analogy, what do we do when our one-bed apartment gets noisy and we can't work? We go to the library, which is more spacious and quieter. Same thing here. What if there was a trick that could transport you from the 3D world to a space with infinite dimensions? So this is actually possible. This was possible several years ago. So there was something called the Indian rope trick in many years ago. So the idea is basically like this. Somebody, the performer throws up a rope into the air, and another performer climbs up the rope. And lo and behold, after climbing a few steps, he disappears into thin air, into infinite dimensions. He does not come back. So that is the Indian rope trick. So can we do something like that for support vector machines? So, or even better, can we come up with something that will let us work in infinite dimensions? That means get all the benefits of infinite dimensions without even visiting the space. Isn't that cool? So that is what we are going to do now. So this is a nonlinear data, right? We cannot separate the data using a straight line. So the shape is nonlinear, right? So that is this is our problem now. We want to come up with the support vector machines, which will come up with this kind of a separation. So the idea is like this. So take, for instance, this data on in one dimension, right? There are some red points and there are some blue points, right? So the data is linearly separable, right? You draw a line here and it gets separated. But if there are some blue points in the middle of the red points, then the data is no longer linearly separable. You cannot draw any line. So this is a one-dimension case, easy to understand, right? So how do we separate this? One idea is come up with a second dimension called x square. Plot x square on the y-axis and x on the x-axis. So then the points end up in a parabola like this, and you can draw a line like this which separates the red points from the blue points. So that is essentially the idea in nonlinear support vector machines. So this is the case when the data is completely nonlinear, not when slightly nonlinear. If it is slightly nonlinear, we can tolerate some slack and use the zeta i's. But if it is completely nonlinear, we use these kind of transformations. So when we map this kind of a nonlinear data set to 3D, 3 dimensions, so this was a 2-dimensional visualization. Now when we map it to 3 dimensions, we can visualize that the points separate out and the surface, the shape in 2 dimensions is now a surface in 3 dimensions. It separates the 2 sets of points, right? So that is the idea. So when you map from 2 dimensions to 3 dimensions, this is how it looks like, right? There's a side view. So this is quite common, right? We do this in engineering drawing quite a few times. Mechanical engineers and civil engineers can very well relate to this. So a blueprint of a building, for instance, is a 2D map of a 3D object, right? So same thing is happening here. Now, what is the mathematical basis for this? So there's something called Cover's theorem. So Cover is just 15 miles away. He was teaching at Stanford. He was a professor at Stanford. And he came up with this theorem. The proof is not too hard also. It's not too difficult to follow, but for sake of time, we'll not go over the proof. But so he kind of proved, this whole paper is summarized in this slide, right? Given a set of training data that is not linearly separable, one can, with high probability, transform it into a training set that is linearly separable by projecting it into a higher dimensional space via some nonlinear transformation. So that is the idea. Cover has formally proved. I think he lived till 2012, I believe. He passed away recently. Okay, so a little bit of illustration here. So you see a bunch of points on the left-hand side. We apply a transformation phi, right, to convert this data into 3 dimensions, and then it becomes separable in 3 dimensions. So how do you do that? What is phi? What is phi? Right? So 2 dimensions, consider them as x1 and x2. Oh, sorry, this should have been y actually. My bad. This should have been y. So 2 dimensions are x and y, or you can consider it as x1 and x2 and consider y as x2 basically, and x as x1. So either way it's fine. So the transformation function can be expressed like this. So the first dimension is x squared, the second dimension is root 2xy, third dimension is y squared. When you apply this transformation, then this is what will happen. So this is not too difficult to see. Why? Because what is the shape of the boundary here? It is almost like an ellipse. And what is the shape of this transformation here? X squared plus root 2xy plus y squared. It is like an ellipse. So you're basically converting the nonlinear shape into axis. You're basically incorporating the nonlinear shape into the axis. So in 3 dimensions, what does this look like? It looks like a plane, the equation of a plane, right? Z1, some k times Z1 plus k times Z2 plus, or A times Z1 plus B times Z2 plus C times Z3 is like a plane, right? So that is the idea here. So in mathematical terms, so the 2 dimensions, x1 comma x2, get transformed to these 3 dimensions. And if you sum up z1 and z2 and z3, you will end up in the equation for the hyperplane. z1 plus z2 plus z3 is equal to some constant, right? So a elliptical shape in 2 dimensions is looking like a straight line in 3 dimensions. Straight line in the sense plane, straight plane. In a straight line equivalent in 3 dimensions is a plane, right? So it becomes a plane here. So you substitute the same thing in 2 dimensions, you get the equation of kind of an ellipse. But the question is, how do you find the phi mapping? So that's the question, that's the problem. We'll come to that later. But let us look at a small visualization. So I got this from YouTube. I thought I will explain, it'll give better insight into what we talked when we view this. So we have data in 2 dimensions, the blue points and the red points. And when you map it to 3 dimensions, it becomes separable, right? So the hyperplane, or rather plane, you can see the plane cutting the cup, and then you see the blue point separated from the red points. So that is kind of the intuition we have. So at this point, it's a good idea to take a look at the math and a great quotation that Lagrange himself made. So the ordinary operations of algebra suffice to resolve problems in the theory of curves. As long as algebra and geometry have been separated, their progress has been slow and their use is limited. But when these 2 sciences have been united, they have lent each mutual forces and have marched together towards perfection. So that's a great quotation. And so that illustrates the power of linear algebra, which is the happy marriage of geometry and algebra. And no wonder that linear algebra is the foundation of machine learning, quantum computing, and all advanced topics. And interestingly, one other note is that Lagrange, along with Laplace and Legendre, was in the doctoral committee of Fourier of the Fourier series fame. So as you can see, things are quite related, right? So we can connect one topic to the other now. The inventions of these 4 mathematicians. Okay, a different perspective of Convex theorem. So essentially, machine learning is all about fitting a curve. In fact, some call it just curve fitting, which we study in mathematics. So we fit a straight line if the dependencies among the data are linear, say y is equal to mx plus c. But if the data is nonlinear, say if the data can be modeled by y is equal to mx squared plus c, how do we do this? how do we come up with a linear classifier? So we basically export the data to a different space where the new x-axis is mx squared plus c, right? Then y dash, the new y dash will be equal to x dash, right? In the new plane. So it will again be back to a straight line in the new coordinate system. So that is the idea. That is basically what we did in Hilbert's theorem. I mean, not what we did, but that provides you the intuition for Hilbert's theorem, right? When you express x dash as whatever was y in the previous model, you basically come up with a linear classification. So that is the idea. So support vector machines essentially finds f of x by transforming the data to a different space. So here's a nice illustration again I found, which talks about the transformation to higher dimensions. So when you transform using a phi function, transformation function, you can separate it using a straight line. Now, all is good when we listen to it, but when it comes to implementation, there are some problems. What are the problems? So if there are 1 million training samples, we need to evaluate the function phi at 1 million data points. And then if the transformed space has 1 million dimensions, we need to evaluate dot products across the 1 million dimensions. 1 million is not an exaggeration. Take the case of an image, right? An image has 2 megapixels typically, right? A simple image. If each pixel is considered a dimension, remember we talked about support vector machines being useful for image classification. Of course, there's a feature extraction process and all that, but I'm just giving you an example just to visualize. So 1 million dimensions is not too uncommon to visualize. So if you have to compute dot product across 1 million dimensions, it's going to be a real problem. It doesn't scale well. So it's computationally infeasible. That's one set of problems. And the other set of problems is not all transformations apply. Right? If you look at this data, red points in between the green points, obviously a straight line does not apply. See, x plus y does not, you'll get 4, 4, 4. You sum up x and y, you get 4, 4, 4. You sum up x squared plus y squared, you can easily separate out. They become 10 and 10, and then you can easily separate out. xy also separates them out. But so what does it tell you? It tells you that some functions work and some functions do not work. Now, how are we going to find which functions work and which functions do not work? So these are all the problems. How do we solve the problem? So an analogy is how long does it take to train a model in self-driving car to recognize objects? Probably takes several hours, right? Probably because it requires billions of miles of data, right? So obviously, and how soon should it do the classification? Like for instance, if there's a pedestrian coming in front of the self-driving car, how soon should the classification come? In microseconds. Otherwise, there could be an accident, right? So how do you match these two things? The way is to save the model. Don't process the data entirely. Only keep what you need from the data and throw away the remaining data, right? And use only the limited data when it comes to processing new data. So capture only the core or the kernel and leave the rest. Capture the core of the data, or the kernel is basically core, right, in English. So leave the rest. So remember in our math that we discovered, came up with, only dot products were in the dual formulation. Eventually, only dot products appeared everywhere in the equations. So we just need the dot products. right? A gram matrix of inner products in the transformed space is all we need. Remember, dot product is a special kind of inner product, right? So we need a gram matrix. Gram matrix is basically a matrix of inner products like this. But because it needs to be in the transformed space, we apply the transformation function phi, right? So we just need this matrix of the inner products, similarities between two data points. Dot product is nothing but similarity, right? Inner product or dot product tells you how similar 2 points are. So now, with this idea, how do we simplify the gram matrix computation? Remember, computing this matrix is really very computation intensive. So how do we simplify the computation? How can we avoid the computing costs of the transformations and the inner products? So what if we found a function k, which represents the inner product in the transformed space, but it takes as arguments only the original feature vectors, but it computes the inner product in the features in the transformed space for all features in the original feature space. Xm and Xn are in the original feature space. Phi of Xm and phi of Xn are in the transformed feature space. So what if we found a function k? So that would greatly simplify our computations. We can compute k in the original feature space without computing phi's or their inner products. But remember, k is representing a gram matrix, right? So it should follow, it should satisfy the properties of a gram matrix. And gram matrix is basically a matrix of inner products. So that is something that we need to spend some time on. And once you find k, classification is quite simple, right? Classification is basically computing the sign of the Lagrange multipliers multiplied by yi times the transformed dot product. I mean, dot product in the transformed space, which is equal to the kernel function multiplied by Lagrange multipliers multiplied by the actual variables, actual classes. So the idea of kernel function is that the kernel gram matrix becomes a function. So remember, we talked about infinite dimensions and all that. So as the dimensions of this matrix become infinite, as L tends to infinity, the above infinite dimensional matrix can be represented by a function, provided the function follows the same properties as a gram matrix. What are the properties? I mean, first thing is, first and foremost is we need an inner product space. So that means we need a set where inner products are defined properly, and then the space to which this function maps should be complete. So that's what brings us to Hilbert spaces. Remember, we said that the dual is in the Hilbert space. So that's what we are going to do now. So each element of the Mercer kernel basically lives in the Hilbert space. Yeah, space is basically like a set of set in the set theory. So kernel functions represent inner products in the transformed space. So they need to satisfy the properties of inner products. So what are the properties? One property is symmetry, right? So the dot product or the inner product of x1 comma x2. I'm using inner product and dot product interchangeably because of simplifying things, because many listeners would be familiar with dot product than inner product. So that's the reason why I'm using them synonymously. But there is a difference. A dot product is just one kind of inner product, right? So the inner product needs to follow the symmetry. That means x1 comma x2, inner product of x1 comma x2 is equal to x2 comma x1 inner product. And the other interesting property is that of positive semi-definiteness. So remember, we define the norm based on the inner product of the vector with itself, right? Similar thing applies to the inner products in function spaces as well. So the inner product of 2 points in the function space should also be greater than or equal to 0. So what does it mean? It means that the gram matrix, which is basically a number of inner product values of inner products, also has to be symmetric and positive semi-definite. So if the matrix is semi-definite, positive semi-definite, eigenvalues of the matrix are non-negative. That's what it means. But we'll look at it in a little more detail in the next few slides. So that brings us to the Mercer's theorem and Mercer's conditions. For a kernel function to truly map to an inner product, the kernel gram matrix must also be symmetric, like we talked. So the kernel function of x comma y should be equal to the kernel function of y comma x. And the diagonal elements represent the squared norms, therefore must be positive. Right, the diagonal elements are basically k of x comma x for various values of x, so which represent the norm, and the norm has to be positive, so the diagonal elements must be positive as well. So positive semi-definite implies positive semi-definite matrix implies if k is the matrix or k is the function. Let us consider matrix first, gram matrix. For any vector v, the transpose of vector v times k times the vector v, a dot product, this is all, should be greater than or equal to 0. So the same thing can be written as, remember, if we had values of the form alpha I, you would end up in this kind of an expression. Right, there will be double summation, and you will get alpha I, alpha j, multiplied by k of x I comma xj, and this has to be greater than or equal to 0. So, and the other way to put it is, its eigenvalues are non-negative. Now, every book says that the gram matrix and the kernel function needs to be positive semi-definite, but so let us also see why they need to be positive semi-definite. So why should they be positive semi-definite? So suppose the phi x is basically x. That means there is no transformation, just linear transformation. Then the kernel matrix or the gram matrix can be defined as the transpose of the feature data set. I mean, the training data set. X is the training data set here. Of course, removing the y classes. The last column is removed. It's basically a series of rows of feature vectors. So from the training data set. So X transpose X, right? So that is the whole idea of kernel, the matrix. It's almost like a covariance matrix, but transposed. So you're basically the kernel gram matrix can be written as X transpose times X. So where X is the training data set features. Now let us consider any vector v with elements alpha I. Then this expression v transform kv can be written as k can be replaced by X transpose X from this, right? And you combine using associativity. You combine, you multiply x with v and take its transpose. Remember, when you take the transpose, the order gets interchanged, and then xv as the other product, right? So what is x times v? What is the final output of x times v? You'll get another vector, right? Call it ut. Right? X times v is a vector called u. So the result will be transpose of u times u. So which is basically a, by the definition of inner product, it has to be greater than or equal to 0. Because if it's a dot product, it has to be, it represents a norm and it has to be greater than or equal to 0. So in other words, v transpose k times v should be greater than or equal to 0. And when you express it in terms of alphas in the which are elements of v, you get this expression. Remember, two summations, because it's like multiplying a plus b plus c times d plus e plus e plus f. So you get all possible combinations of the variables. So this logic applies to covariance matrix also, because the covariance matrix is also one kind of gram matrix. So it also has to be semi-positive definite and things like that. But anyway, covariance matrix is not part of today's talk. Now that brings us to the actual Mercer theorem. Mercer theorem states that given a function k, which takes two arguments. Actually, they need not be real numbers, but for simplicity, let us consider real numbers. So the real number, two vectors basically. R power n is basically a vector, and so the domain is the product of two vectors, inner product of two vectors. So, and it maps to a real number. So k is a kernel function which maps inner product of two vectors to a real number. That's what this first thing means. So let k be given to us. Then for k to be a valid Mercer kernel, it is necessary and sufficient that for any finite number of vectors, the corresponding kernel matrix is symmetric, positive, semi-definite. So if you are able to prove that the kernel matrix is symmetric, positive, semi-definite, then it is a valid kernel. And for Mercer kernels, it is proven that there exists a transformation function phi such that the kernel of two vectors is the dot product or the inner product of the transformed vectors. Isn't that cool? So now we are solving our problem. We now came up with a function which can express the inner product of two vectors in the transformed space. So all we need to find is a function which meets the Mercer's conditions. That is, it is positive, semi-definite. So that is a kernel trick. So the kernel trick is basically take nonlinear data, say in this example, one dimension, and apply a mapping, in this case, x comma x squared, such that the dot products of the new transformed vectors can be expressed as a kernel function. So the dot product or the inner product of the transformed vectors can be expressed as a kernel function. And in this case, we applied a two-dimensional or the squared transformation. So we get this. So that's the kernel trick in essence. Now there are several kernels. The first example of kernel function is the polynomial function. So polynomial kernel with degree d and constant c, like we saw in the previous case. Previous case there was no c. It was just c was equal to 0. But the general form is when there is a c constant, it can be written like this. This first equation here. And what does it look for when d is equal to 2? Similar to what we saw earlier, but only thing is there is a c here, so that's why we get 6 terms. So we map 2-dimensional data to 6-dimensional space if we adopt a second-degree polynomial kernel. So the explicit feature transformation consists of all polynomial combinations of individual dimensions of degree up to d. So that's what we see here. Now, what if the data is extremely nonlinear? If you look at this figure, the data is, it's hard to even model it using a polynomial or anything. It's really very nonlinear. How do we deal with this kind of a thing? So can we separate the classes by exporting to, say, 3 dimensions or n+1 dimensions? Probably no, right? So we might probably need infinite dimensions. So that's where our infinite dimensions things come. So that's where what is called as the RBF kernel comes into picture, radial basis function kernel. So it's almost like if you know k nearest neighbors algorithm, it's almost like k nearest neighbors algorithm. All points are support vectors in infinite dimensions. So essentially it will form circles. The decision boundaries are like circles like this, radial. Circle has a radius, so it's radial. So how do we come up with these kind of decision boundaries? We apply a different kind of kernel function called the RBF kernel. So RBF kernel, the formula, the equation is given at the top. And if you remember probability theory, you can as well relate this expression to the probability density function for normal distribution, a bell curve like this. So x is the point, and x dash could be the test data. So the kernel between x and x dash. You can also view kernel as a weight, right? Remember, we talked about attention model. We are giving some weight to points, support vectors. So you can think of kernel as a weight you are attaching to the point, to the test data, or to the data in consideration, right? So this is represented by the something like the PDF of the probability, the normal distribution. So what does that tell you? It tells you that as you move away from the point, the influence of the point reduces. So if the test data lies here, the influence of this point is really high. The test data lies somewhere here. It may not be all that important to this point, right? So that is the intuition behind RBF kernel. And as you can see, the influence of every point in the training data set is in the form of a circle, radial. The influence is radial. It is better illustrated like this. So the influence of the point is really high in the center, and it wanes exponentially as the point moves away. So the value of RBF kernel is maximum at the center, where the distance is 0, and it reduces with the distance exponentially, right? So, and if you know KNN algorithm, it is something like KNN, right? KNN, what does KNN do? It tries to find the nearest neighbors. So it's like weighted KNN. So you're defining a neighborhood of influence, and that influence reduces exponentially with distance. So we can think of it as a weighted KNN as well. Now, let us take an example. This is from a textbook by Professor Han. It gives you some grounding into what RBF kernel looks like. So Gaussian radial basis function is represented like this. And suppose there are 5 original 2-dimensional points given by these coordinates or couples. If we set sigma to 4, we can compute the gram matrix like this. The right side table is a gram matrix, and the left side is the original feature space. So original feature space, transformed feature space. So this is just an example. Again, we are not going to compute. The right side is the inner product of the transformed space. It's a kernel function, right? So, so these kind of kernels where the influence depends only on the distance, on the difference vector rather, separating the 2 data items. These kind of kernels are called stationary kernels. So remember, we are doing x1 minus xi comma xj. So it depends only on the difference vector. So these kind of kernels are called stationary kernels. So there are a number of kernels. Proving that a function's kernel is slightly out of scope, particularly since we are out of time also. But I just wanted to show this cool demo from, I think, Karpathy. I think this demo is by Andrej Karpathy, I think, right? Stanford, yeah. So, so this is a cool demo. You can adjust the C. Remember, C is the soft margin hyperparameter. You can adjust. I'll try to add some points here and there. Highly nonlinear. As you can see, they start forming shapes. And as I add points, the decision boundary reduces, right? So as you can see, it's forming circles. So this is basically the radial basis function. And the hyperparameter there was sigma, right? The denominator, the variance. So the variance kind of determines the influence, right? As I decrease the sigma value, the radius decreases as well. And similarly, you can look at the function of C. If you increase C, then it's almost the margins also increase. And beyond certain point, the margins don't increase. But if you reduce C, the margins reduce as well. Remember the trade-off we talked about? So that's a cool demo I thought I will show. So there are a number of kernels. So I listed a few kernels. We saw polynomial kernels already, complete polynomial kernels. So polynomial kernels, C is equal to 0, complete polynomial when C is a constant, RBF kernel is exponential, and so on and so forth. Now, how many dimensions? So polynomial kernel, we saw from the previous slide, number of polynomial terms, right? It's a combinatorial of these terms, right? So that is the number of dimensions. But for radial basis functions, I said that it's infinite dimensions. That follows from the Taylor series. Remember, e power x is equal to this sequence at a is equal to 0. So this basically, you can think of them as infinite dimensions, infinite polynomials, right? So follows from the Taylor series. So you can think of it as sum of polynomial kernels. You're arriving at a kernel by adding multiple other kernels, and in this case, it is infinite number of kernels. So in summary, the kernel trick is basically replacing inner products in the original space x and x dash with a call to the kernel function k, x comma x dash. The kernel k can be written as a dot product or inner product of transformation functions as phi of x transpose times phi of x dash. So in effect, we have transformed the original feature space, the kernel product or the inner product in the original feature space into the inner product in the transformed feature space without actually doing the transform. So I kept my promise. I said that we will not visit the infinite dimension space and get all the benefits of the infinite dimensions. And that's what the kernel trick basically did for us. So transforming the data in original feature space X to data in transformed feature space in higher dimensions without actually visiting the higher dimensions. So a nice quotation I found, I thought I would give this quotation from a newsletter. Support vector machines are a rare example of a methodology where geometric intuition, elegant mathematics, theoretical guarantees, and practical algorithms meet. So this is from the researchers Bennett and Campbell, Christine Bennett and Colin Campbell in 2000. I quickly want to close the discussion by relating support vector machines to other machine learning. So first is Kernel. We already talked about it, but in terms of the algebra, if you look at the classification for support vector machines, this is what we arrived at, right? So it is basically k times alpha I times yi times k times the kernel function. So if fx is greater than 0, then the actual label for y for the data item is 1 plus 1, otherwise it is minus 1. And alpha is equal to 0 for non-support vectors. So this formulation, if you look at all this, alpha I can be viewed as a weight or a relative importance for each support vector. So this is basically instance-based learning, similar to KNN. So here the instances are support vectors, right? So that's how you can relate support vector machines to KNN. And how about regression trees? So regression trees form regions like this. So they are hypercubes. In two-dimensional case, they form straight lines, but in multi-dimensional case, the decision trees form hypercubes. So each hypercube can be considered as a region and as a decision split. So the value associated with each region of the points in that hypercube is the y. So if it is a single feature, just to illustrate the concept, if it is a single feature, what we can probably do is we can bin the data, binning, and taking the average of the bins. So if you take averages, you'll probably end up in a decision boundary like this, a regression line like this, right? So the goal is to find the splits that minimize the MSC. So that is the goal of machine learning. So you can think of kernel functions, support vector machines using kernel functions as smoothing these regression lines so that the MSC is minimized. and the decision boundary is smoother, right? So if you take, for instance, the RBF kernel or sigmoid kernel, we'll probably end up in a more smoother kind of regression line. So that is, in algebraic terms, if you look at the how you predict the target variable fx is equal to y, is by using this formula, right? You try to sum up all the values of y in a region, in that particular region, right, hypercube, and take its average and divide it by the total number of items in that average, right? So that's how you come up with a, you do the prediction in regression trees. So compare this with support vector machines. Very similar, right? Quite similar. So you have only thing is there are weights attached to the points. In this case, the weight was 1. This is an indicator function. It gives a 1 or a 0 if the point is in the region. But here we have a weight. And how about RBF neural network relation to deep learning? So RBF neural network is basically given as a sum of the weights multiplied by the RBF, right? And you can see a direct relation between this and what we do in support vector machines, right? So support vector machines, that is the reason why is an important concept in machine learning. It lays foundations, or it's a good way to understand other algorithms also. And you have the mathematical grounding if you study support vector machines. There are many more parallels. We already talked about attention mechanism and things like that. So please feel free to contact me anytime. I have a web page. You can search me on Google. And any questions? Let me check. There are no questions on Zoom. Let me check on YouTube. Okay, there are no questions on YouTube either. So I think we are good. So thanks everyone for joining. And I know it's really late, so I appreciate your patience. And